Hello everyone, welcome back. Last class we derived relation between before and after properties across an oblique shock, where we still had the variables theta, beta and m1 not linked fully. Okay. We got a relation in terms of rho 2 by rho 1, and then we said if we know u1 normal or m1 normal, the normal Mach number with respect to that oblique shock normal to that, if I can get that, then I can go to normal shock tables for that particular gas, then I will just get all the properties across that. We said that, and we tried to get that angle beta in terms of the deflection angle theta for the given Mach number. That is where we stopped. So, we will continue from that point. So, we derived this last time. We had this, and we said rho 2 by rho 1 can be obtained from normal shock tables or normal shock relations, substituting it with m1 normal instead of m1. So, I will write my rho 2 by rho 1 from the previous thing. You have one page of it. If you go back to that page, you will see this formula. I am just replacing m1 with m1 normal. I will replace m1 normal with the expression for it which we derived last time, which is m1 sin beta. So, it will be m1 sin beta whole square, which is m1 square sin square beta. Again there will be gamma minus 1 m1 square, it will become m1 square sin square beta. Now, our job today is to substitute this inside this rho 2 by rho 1 and here, and simplify the expression, so that we will have something very easy to work with. It may not be very easy, but it will be simple enough to work with. That is the goal. Okay. So, let us start substituting inside that. I will directly start with rho 2 by rho 1 minus 1, where I will put minus 1 here, multiply this with that and ignore the denominator. I will do the same thing here, multiply this tan square beta with this denominator and then keep only the numerator here. Both will have common denominators exactly the same. I will not write that expression because they will get cancelled anyway. Now, we will start writing. So, it will be rho 2 by rho 1's numerator sin square beta, that numerator minus the denominator is minus the denominator, this whole thing multiplied by tan beta. That is the numerator of that function, whole thing divided by, of course, we still have the denominator for this numerator. We will not write that because the same thing will get cancelled in the bottom. Tan square beta times denominator of rho 2 by rho 1, that is this. Tan square beta 2 plus gamma minus 1 m1 square sin square beta. This plus numerator of rho 2 by rho 1. Now, this will be the simplified expression. Both the numerator and denominator will have this in their denominator. If I write the original thing, I will not write it, I have just cancelled those, let us assume. Okay. Now, we want to simplify this expression overall. Okay. First simplification which I want to do is, I want to take this tan beta to the denominator. So, I will simply wait, let us not do it that way. Let us because this does not have a tan beta in there. So, I will rewrite this as I want tan square beta taken common for the whole denominator. So, I will just rewrite this as cos square beta into cos square beta. If I do this, now I have tan square beta in here. So, I have tan square beta common for the whole terms in the denominator. Now, I have 1 tan beta in the numerator, they will get cancelled. So, now I will go write the next expression. So, I do not have the tan beta anymore in there. Okay. Instead, I have cot beta, which is coming from the denominator tan square beta. Okay. Multiplied by m1 square sin square beta minus 2 minus gamma minus 1 m1 square sin square beta. I have written the square bracket more open, divided by bottom will be 2 plus gamma minus 1 m1 square sin square beta plus gamma plus 1 m1 square cos square beta. Okay. Now, this is what I have. I want to simplify this expression inside this flower bracket. Okay. If I look at this, there is a gamma m1 square sin square beta, and here there is a minus gamma m1 square sin square beta. I can just cancel them directly, and I will put this arrow as usual to link that this is how I cancelled it. Okay. Now, the next term m1 square sin square beta with a positive sign, here again it is positive m1 square sin square beta. So, it will be 2 m1 square sin square beta. The only thing remaining is minus 2. So, I can take a 2 out common, and I will write this as 2 cot beta multiplied by m1 square sin square beta minus 1. That is our numerator. Now, in the denominator we want to again do the same thing, gamma m1 square sin square beta, gamma m1 square cos square beta, they are not the same, but you know that sin square beta plus cos square beta is 1. Okay. So, I can write it as 2 plus gamma m1 square with sin square beta plus cos square beta, and of course, we know that this is equal to 1. Remaining terms are minus m1 square sin square beta plus m1 square cos square beta. I will write it as plus m1 square cos 2 beta. Hopefully, you remember this formula from trigonometry. It will become cos 2 beta. Cos 2 beta is equal to cos square beta minus sin square beta. So, I will get to that form from here. So, I have my final expression. This is the final form, cannot simplify it any further. So, I will have tan theta equal to 2 cot beta multiplied by m1 square sin square beta minus 1 divided by 2 plus m1 square times gamma plus cos 2 beta. This is the expression I have, okay, and very essential expression for oblique shock problems calculations, okay, very important. This is what is linking the deflection angle, shock angle and the incoming Mach number. They are related by this expression. Now, let us say I have a problem where I know that the shock is having a particular inclination to the incoming flow and it is having an incoming Mach number some value, then I can calculate the deflection angle directly from this formula. But in most of our engineering application, we will have the opposite. We will have a case where I will be given the theta I will be knowing the Mach number, that is I know my body shape, I know that the body is tilted to the flow with some angle. So now I have to find what is the shock angle there, because only after I find beta I can go and calculate any property, right. I need to know m1 sin beta, that is a normal Mach number. Once I know that, I can go to normal shock tables to find out properties across the shock. So I need to know the beta, that is what will typically be the problem when we are solving in engineering. So given a theta and m1, I need to find a beta. Now I have to invert this relation, it is not very easy. So we will go use the age old method of using a plot, using graphs. Okay. So let us go to that screen. So what we are seeing, I do not see the mouse first, okay. What we are seeing here is shock angle beta going from 0 degrees to 90 degrees and the deflection angle theta in degrees again. Okay. I am plotting it for oblique shock gamma equal to 1.4. Of course, I could get the whole plot for some other gamma value, we are using this because it is the most common thing. The plot looks like this, it seems like for every deflection angle there is double value for any given Mach number. These values written here 1.1, 1.2, 1.4, all this up to infinity, Mach number infinity, everything, it seems to be a inverted U shaped curve, which is for every deflection angle, let us say I pick 10 degrees and I go for say Mach 2, I could have an angle of the order of 39 degrees, or I could have an angle of the order of of the order of 84 degrees or so. Okay. I could have two different values like this. So which means I am going to have two different shocks. Okay. I could have a shock that is having a low shock angle or a very high shock angle. First observation we are making. Okay. We will make more observations. I just wanted to plot this, I do not want to use this plot to explain things, I will go and draw this on the board and explain things. Okay. But one more thing to note, it has a peak value for every Mach number, and above that we cannot get a solution for beta. Okay. That is what you are having, and beta does not have a value below a particular Mach angle, below a particular angle, it so happens that it will become Mach angle, we are going to look at that now. And I have also drawn one more line here, we will come back to this line later. On the left of this line it is supersonic, and to the right of it, it is subsonic, we will get back to that later. Now we will go back to the board and look at the same expression again. Okay. If I will go back to this itself, it is enough if I look at this. Okay. This expression, denominator cos of 2 beta, where beta is going to be anywhere between 0 and 90 degrees, right. If I think about it, 2 beta will be anywhere between 0 to 180. Okay. So there will be some values for which this will become minus 1, some values for which it will become plus 1, but gamma is always more than 1.1 or more than 1. So this whole function will never ever become negative, this is always positive. M1 square is positive, 2 positive, everything is positive. Okay. Now I want to find values where the curve hits 0, where theta will become 0, no deflection angle, that is what we are looking for. Okay. We will see why. So only the numerator can go to 0 now, denominator is not going to go to infinity really. Okay. If at all Mach number going to infinity, we will come to that special situation later, because if it is going to infinity, numerator also has a m1 square, it will not really go to 0. Okay. So now I have to think about other reasons why it will go to 0, either the square bracket can go to 0 or cot of beta can go to 0. If cot beta is 0, tan beta tends to infinity, which means beta is equal to 90 degrees, not tends to, it is equal to 90 degrees. Okay. That is the way we write it, and the other expression will tell me m1 square sin square beta equal to 0, this minus 1 equal to 0 is m1 square sin square beta is 1. So I will take a square root of that, it will still be 1, plus minus 1, minus 1 is not possible. So, we will keep it as plus 1. Minus 1 just simply means that the flow is from right to left instead of left to right. Okay. Mach number negative does not make sense for us, it is just absolute value of velocity for us. Okay. So, I will just have one solution for it, m1 sin beta equal to 1. Minus 1 just simply means that I have either a negative angle beta or I have a negative Mach number, which means flows from right to left. Okay. Negative angle beta is the shock, instead of like this it will be like this, that is all, that is nothing great. So, we will come to that situation later, we will not call it negative beta anyway, we will keep it like this. So, this implies that beta is sin inverse of 1 by m1, which is your Mach angle. Okay. So, we are finding that we have solutions for beta anywhere between this to this. What if, oh, I did not, I just jumped ahead of myself. What if my beta is less than this value? If my beta is less than this value, then I am going to have sin square will become lesser than that value, right. Sin is an increasing function from 0 to 90. Okay. It will become less than that value, which means m1 square sin square beta minus 1 will be less than 0, it will become negative. That does not mean anything here, theta will become negative, we cannot tell anything special here. Let us go one board back, we have this expression here. Okay. No, I will write a better expression, P2 by P1. Let us go to a fresh page. We will write P2 by P1 for oblique shock. Of course, it is going to be written in terms of m1 normal. I will write m1 normal equal to m1 sin beta. We already have this kind of expression written before, so I will just write it directly. Here it will be I will get this. It used to be m square minus 1, it just comes out to be this. Okay. So, now I will go look at that and say, if my beta is less than mu of m1, mu of m1 is your sin inverse 1 by m, right. So, if I have such a situation, then this whole bracket, square bracket, will become negative. If this becomes negative, I am going to have a condition where 1 minus 2 gamma by gamma plus 1, which means multiplied by some other number, that is fine, but it is 1 minus something, okay, which basically means that P2 by P1 will be less than 1, okay, which means it is becoming, it is still a shock in our case, but it is a shock which has P2 less than P1, which means it is a expansion shock, which we already disproved long back in normal shock situation, where we said that delta S by R for those cases will be less than 0. Okay. So, I can say that for beta less than this, I will have P2 by P1 less than 1, which means it is expansion shock, which will have delta S by R less than 0, not possible. So, I will never have a situation where beta is less than my Mach angle for that particular incoming Mach number m1. Okay. So, now my solution exists somewhere between mu of m1 to 90 degrees, which is what we are seeing in the plot anyway. Okay. So, now we will go draw the plot once more. I will draw it on a fresh page, I want to draw it big. These are beta, this is my 90 degrees, and here this is 0 degrees and these are theta. Okay. And for a particular Mach number, it is going to do something like this. Okay. For another Mach number, higher Mach number, it will do something like this. It is supposed to reach the same point. Okay. It is m1, m2 greater than m1. This is what it will do. Okay. So, now we can already say, we already proved that for a given Mach number, it goes from mu 1 which is our sin inverse 1 by m for that m1 to 90 degrees, that is the only place where we will get any solution. Now, we will say one more, for any particular deflection I get two values. Now, I have to label them separately. So, I will call this the weak solution, not for no reason, but I will tell you the reason after writing this. Okay. And this side is the strong solution. Before the peak it is weak solution, after the peak it is the strong solution. We will keep it like this. Why is it called strong and weak? We will go back to our P2 by P1 here. Okay. We find that beta is anywhere between mu 1 to 90 degrees. In this place sin beta is a increasing function continuously, which means if I have a higher beta I am going to have higher P2 by P1, which means it is more compression. That is the reason we are going to call lower beta as a less compression shock, higher beta as higher compression shock. So, I am going to have strong shock and a weak shock, two solutions are possible. So, I am going to this plot and I am going to say this is my weak shock solution, this is a strong shock solution. Two solutions are possible, one is weak shock, other is a strong shock. If you look at the curve, it is not like a simple symmetric parabola, it is shifted, skewed more to the right, that is what it will look like. Okay. Now, if I want to find the maximum value, the beta for which theta will be maximum, if I want to find that, of course I can go and derive it, it is just derivative equal to 0 you have to set. Let us say we will not do that, I will give you the expression here. Okay. I can find the beta at which you will have maximum for any given Mach number, and that is given sin square beta at theta equal to theta max is given to be I derived it, if you want you can go derive it, I do not think it is needed to be derived in our class time. And it is not very difficult to derive also, it can be derived. I have to close bracket. Okay. So, this is the expression we have. Okay. So, this is only a function of gamma and m1, nothing else. Okay. Gamma and m1, it is going to give me a beta. Now, I have to go use this beta in our tan theta formula to get the maximum theta. Okay. I will not do that, you guys can do it, I will just leave it for you to do it. Okay. So, now the next thing I want to talk about is the other line which we looked at in the plot. We had one more line which was going like this, while the other line was your theta max line that was going like this. This is your theta max line, it goes through for all Mach numbers the peak values, it goes through all of them, that is one line. The other line is to the left of it, remember that it is at a lower beta value, and that is your m2 equal to 1. Okay. I actually did the calculation for all Mach numbers for all betas and found the m2 for all of them, and then put a contour of that along here. Of course, you can find an expression for when m2 becomes 1, it is not simple enough. So, I just did the graphical method, it is easier for me. Okay. I just did this. What you have to note is, if I think about a strong solution, strong oblique shock, then I am going to have only subsonic condition here behind the shock. If it is weak, for low values of my theta, I will have supersonic flow behind the weak solution, behind the weak shock solution, if you want to think about it. Why do I call it solution suddenly? It is the solution to our equations and it gives two answers. So, I call one of them weak solution, other a strong solution. Okay. So, I am basically having a weak solution for low thetas, it will have supersonic flow behind. For thetas very close to theta max, typically that is the case. When theta is very close to theta max, you may have a subsonic solution. You have to be now careful and looking at this, that region. It may have subsonic solution behind the shock. Okay. You just have to be careful about it a little bit. Okay. Now, I want to look at why can there be two solutions for the same deflection. Okay. So, we will go to that side and we have to start drawing pictures. So, let us say I have a very long vector, that is my incoming velocity vector, and that is parallel to our horizontal, and now I am going to say I have one solution that is at this angle. First watch, then draw, it is easier. I will tell you how to draw it so that it looks like you can always draw it correctly. Okay. But I will also tell you what goes wrong if you draw it too many times. I will draw one more shock angle that is lesser than this angle. This let us call it the strong solution. Now, I will draw another beta weak solution. I have two solutions. Okay. Oh, I have one more color. I will use this color, hopefully it can be erased later. Okay. The pink one is our weak solution, the white is our strong solution. Okay. So, let us look at only the strong solution first. So, I have to figure out the normal component. So, I have to drop a normal for this vector. I am drawing in a particular way so that I will get to the point where it looks like the downstream velocity vector can be drawn. Okay. So, now I have to find that the u tangential should be just translated across that side, that will go to somewhere here on that shock, and now I will draw again normal direction. I am going to say my velocity vector, the final angle is going to be along this line. This is my theta. This is my theta direction. I draw that line also already. Okay. Now, I will say this long vector, which is my u1 normal for strong shock solution, is going to be brought down. U2 by u1 will be less than 1 for a for a shock, normal shock. So, I have to draw something small enough such that it will go meet along that line. I am drawing in a particular way so that it will go along that theta. Okay. So, I will say this is my u2 normal for strong shock, and this is my other tangential velocity. So, now my final vector happens to be this. Okay. This is one possibility. I am saying that incoming velocity is now turned by theta degrees with this beta. I will call this beta strong. With that beta, I am going to get to this. That is one angle. Now, we will go for the weak solution with the other color. I want to do the same thing for this, but the angle is different. So, I have to drop the normal again. I will erase that u1 normal so that it is less confusing. Okay, it is roughly that. I will just extend that normal here, and now I have to say it has to reach that line. Okay. So, I will draw a line parallel to it, and I have to tell that this is my normal, u1 normal sitting here. Okay. u1 normal is sitting here. I have to take this full length of u tangential across there, that will be roughly somewhere here. Wherever it meets there, that is your final point. Just extend that across here. So, now I will just draw the vector slightly shifted so that you know where the other one is, but actually it is supposed to be on the same thing. Okay. So, you are finding that I can draw two solutions which will exactly match. Now, you may ask, if I follow the same procedure, I can draw how many ever shock angles I want with the same angle finally. And if I follow the procedure, I can draw more, the same process if I follow. If I already fixed the theta and choose beta and draw all this, I can do that. But you should know that I do not have the freedom of choosing u2 normal, u1 normal to u2 normal ratio. That is decided by normal shock relations. Okay. It so happens that the relations will permit only two such values, not any angle you choose. That is what your equations are showing, that is what your final plot is showing. Okay. It just looks like we kept it as a free variable, we did not choose this from normal shock. So, I could choose how many ever currently if I want. If I go and tell normal shock can only be two values, that is what it will be. Okay. This is just for people who want to ask different kinds of questions, I just wanted to tell that also extra. Okay. Now, I will tell you one more thing. It so happens that we have two solutions, but in real life we see mostly only weak shocks. If I have a steady problem, I see only weak shocks. Okay. Till now, I have not seen a steady, stable, strong shock solution. Okay. And I have not seen anywhere in literature also stable, strong shock solution. Okay. That being said, that does not mean people have not observed strong shock solutions. They have observed it, but in unsteady problems. That is the idea of stability here. It so happens that it has now been recently proved that recently in the sense it is last year or this year it was proved that the strong shock solution is an unstable solution, while the weak shock solution is a stable solution. Because of that, if there is ever a formation of a strong shock solution, any small disturbance, noise, any small disturbance in the flow will throw it to a weak shock solution. Okay. That is why when we wait for long enough to form steady stable solution, steady state, and we are looking at the problem, we will always see only weak solutions. By the way, stability can go the other side of the mountain also, right. If you think about stability as a ball sitting on a mountain, I can push it that way or the other way. If I push it the other way, it becomes a normal shock or a bow shock. Okay. This is just extra information, you do not need to know it right now, okay. And I am just telling you anyway, so that you are ready for it. Okay. Now, I just want to put some observations in a table form for strong shock and weak shock. I have told you most of them, anyway we will just put them in an order. I like now I want to look at it from the point of view of the tangential velocity, which is caused by our observer moving along the shock, we say. Okay. If I think about it that way, I want to find observer. It so happens that the observer moves fast in a weak shock and in a strong shock slow. Okay. That is, I am having a higher tangential component in a weak shock, lower tangential component in a strong shock, which we just now saw in the plot. Right. It is anyway there. The next thing we want to look at is normal component. U1 normal, let us say, I am looking at U1 normal. U1 normal is low for a weak shock, high for a strong shock. High for a strong shock. Okay. Of course, now you can easily tell beta, we already defined everything based on beta. Here it is less, more. This is how we defined, actually probably this line should be at the top anyways. Okay. So, now the next thing we want to see m1 sin beta, which is your m1 normal, right. Of course, you can tell that from u1 normal I can directly tell that that will be low, but that is not what I am interested in. I am interested in, I will plug this into normal shock, which will give me m2 normal. I am going to look at only m2 normal. M1 normal, you know what it will be, it will be low and high. I do not need to write it separately. I am more interested in this. If my, this you have to remember from normal shock solutions. In normal shock, if my Mach number is low, the m2 normal will be closer to 1. Okay. We know it should be subsonic, but it will be high subsonic. Okay. M2 normal will be high subsonic. While here it will be low subsonic. Okay. Here it will be low subsonic. Now, that being said, I am actually interested in m2, actual m2 value. M2 normal is equal to m2 sin beta minus theta. This is what we know already. This is our formula for it, right. So, if this is the case, now we said that beta is low, theta is the same, okay. And m2 normal is higher, we said, for weak shock. Beta is low, m2 normal is higher, which means m2 must be higher, okay. That is what I am interested in. M2, here it will be higher, here it will be lower. How will I know it is lower for strong? Let us say compared to weak, beta is higher, okay. If beta is higher and this is lower, then to compensate for this increasing and the overall this is decreasing, this has to decrease a lot more, right. So, I can tell for sure that strong shock Mach number downstream will be very, very low. This Mach number is not normal Mach number, this is a full Mach number, okay, including the tangential component, everything together, the actual flow velocity Mach number. Okay. Now, I just want to give you one more feel for things. So, I am going to look at kinetic energy conversion, okay, that is the next thing. Kinetic energy conversion, what is it getting converted to? It is getting converted to internal energy, which is expressed in the form of pressure and temperature. I will say 2 pressure and temperature here. If you are more into molecular gas dynamics, I can tell that it is going into internal energy in the form of translation energy, rotation, vibration, etc. And the pressure is one way of expressing translation energy, that is what it will come out to be. So, pressure and temperature are related through translational mode. That is too much information for our simple gas dynamics course, okay. But anyways, that is sitting here. So, basically I am taking the kinetic energy in the flow and putting it into the internal energy in the molecules. Now, I am thinking molecules, while this is I am thinking fluid element, okay. If I take it and put it inside the molecules inside the fluid element, then I am finding that the conversion will be less for this case and more for that case. How can I say that? I can directly say that u1 normal is higher for strong shock, which is here, u1 normal is higher for strong shock, okay, but the outcome is very small, okay. I am putting it as normal in Mach number terms. Of course, you should know that temperature is also going to be higher, right, because m1 normal, we maybe I should write m1 normal low, high, okay. If m1 normal is high, T2 by T1 is higher. So, temperature of the shock, temperature of the flow behind the shock is higher, but Mach number is lower, which means the velocity is really, really low, okay. Velocity will be really low, okay, which means I start with very high normal component velocity I am ending with very low normal component velocity. What happened to all of that energy which is in the form of bulk movement of fluid, the kinetic energy, they all went into internal energy in raising the temperature and pressure of that fluid. That is why you are having higher temperature and higher pressure downstream compared to weak solution. Okay. So, that is why I am saying this is less and that is more. Okay. This is one set of things we wanted to say. Oh, now I want to look at one thing which is very tricky in solving problems. What happens to P02 by P01? This is just across oblique shock. I am not anymore thinking about just strong shock and weak shock. This is for any oblique shock, could be strong or weak. If I am thinking strong or weak oblique shock, I am interested in finding P02 by P01. Which way should I find it? Should I find it from M1 normal or should I find it from this from M2 and this from M1? Which way should I find it? That is the question we want to ask. Okay. It looks like if I write this expression, this is going to be P02 by P2 divided by, which is based on M2, P01 by P1 based on M1 multiplied by P2 by P1, which is, of course, it does not matter whether it is M1 or M1 normal, we already showed that last time. So, that is here, because movement of the observer does not change the actual pressure jump across the shock, only the velocity components will change. So, it is going to remain the same, that is what we said. Okay. So, that is that case. So, now we want to write the expressions for these. Let us say since I started that, I will write that P02 from M2 divided by P01 from M1. If I expand those terms, it is going to look like M2 square to the power gamma by gamma minus 1 divided by 1 plus gamma minus 1 by 2 M1 square to the power gamma by gamma minus 1 multiplied by, I will just leave it as P2 by P1 from M1 normal. Yeah, because that is going to be the same for both, I do not want to write the expression, I will just leave it like this. Okay. This is from one form. The other form, P02 by P01 from M1 normal, is going to be expanded the similar way. Expanded the similar way, I will write it as P02 by P2 from M1 normal, that is the difference between the previous one and this one, divided by P01 by P1 from M1 normal. Oh, that should be M2 normal, by the way. P02 by P2 is from M2 normal and P01 by P1 is from M1 normal, okay, multiplied by P2 by P1 from M1 normal. If I look at this expression, it is going to look slightly different. I will write it in terms of that M2 so that I can compare the expression. M2 square sine square of beta minus theta. We did this M2 to M2 normal last time. Okay. Whole to the power gamma by gamma minus 1 divided by 1 plus gamma minus 1 by 2 M1 square sine square beta to the power gamma by gamma minus 1 multiplied by P2 by P1 at M1 normal. This is what I have. If I look at the expressions, there is no connection between these really. Okay. They should be very different, right, that is what we see. Okay. So, in my opinion, you should not be using this, but wait, we said P02 by P01 is related to entropy jump across shock. right. We had this formula, I will go back and write that again. I wanted to confuse you a little bit, so I am taking you this particular path so that you will be more clear at the end of it. Okay. We had this formula delta S. We had this formula which we said for normal shocks T naught equal to T naught 1, and so it became log of P naught 1 by P naught 2 for delta S by R. And we said in moving shocks this is not equal to 1, and so we have to keep the whole term. And now in our oblique shock we said we are again in shock fixed coordinates, and the motion of the observer is perpendicular to the fluid motion in that particular reference frame, so it does not change my T naught value, the movement of the observer, the V value does not change the T naught, it is going to be the same across both sides. So we said T naught 2 equal to T naught 1 there also, which means my expression comes out to be P naught 1 by P naught 2. Now that being said, there is one oblique shock, whichever way I calculate there is only one entropy change. Okay. That being said, I can say one of them is correct, other one is wrong, that is also there. But I am going to say one more thing, the change is because of some observer observing it differently, that does not change the fluid's state. Okay. Observer is moving along the shock and looking at it once, other case he is just standing still and looking at it only in the normal component. Okay. Those are the two ways of looking at things, which means the entropy jump across should be exactly the same whichever P naught 1 by P naught 2 I use. Okay. That being said, P naught 1 by P naught 2 by P naught 1 which we derived here, whichever method I use I should get the same expression. Okay. We will go see a numerical example next class, okay. But that happens to be true. That being said, I will still keep the caution that expressions look very different. Okay. In my gas tables I told you already that I have one more P naught 2 by P 1 column. Do not use this column to find the P naught 2, okay, because the P naught 2 from this expression is not the same P naught 2 from this expression. It so happens that the P naught 1 is not same for both also, but the ratios are the same. Okay. If I go and use P naught 2 by P 1, I will make mistakes. In my calculations we used P naught 2 by P 1 for normal shock examples, we did this already. I told I have a extra column in my gas tables, I used this, and we did it without that also, we did it two methods. Okay. So I could do that, but in oblique shocks do not use this ever unless you want to calculate it only by normal this method, M1 normal method. If you are using this and finding P naught 2 and finding P naught 1 based on M1 normal using this kind of method, then you can use this column, otherwise you will make mistakes if you ever take this P naught 2 and say that is equal to P naught 2 for M2, that will be wrong. Okay. P naught 2 for M2 will be different from P naught 2 for M2 normal. Okay. That is what I wanted to say here. Once I say that, then everything else is clear, you cannot use this for my actual calculations. Okay. It so happens that the ratio is matching nicely. If I start from here and use the expressions for M2 in terms of M1, I can go to this form finally. It is a long procedure, I do not want to go through it. If you want, you can go prove to yourself that this is equal to this, or if you want a simpler way to do it, take ratio of this divided by this and prove that this is equal to 1. It can be proved, it is just a very lengthy procedure, I do not want to do it. Yeah, actually it is not very difficult. If I just take ratio of this and this directly gets cancelled, everything has it to the power of gamma by gamma minus 1, I will remove it, the remaining thing must be equal to 1. I have to prove that. Not very difficult, but it is very lengthy. If you finally go and see, it will just come out to be one of the identical normal shock relations which you will anyway have. So, you will say yes, it is identity. So, it is going to be equal to 1 finally, that is what you will end up with. Okay. So, now next class we will go and look at what happens with around theta max, that is the next thing we want to see. Okay. What if my theta is more than theta max, and from there we will go into why is there a theta max, that kind of stuff. Okay. That we will do next class, and then probably some example problems of how to solve oblique shock problems in the next class. Okay. See you people next time.